Hi. Welcome to Astro 101, the Sun and its Neighbors. I'm Professor Bart Netterfield. Can you believe that it's already our 5th lecture? In previous lectures, we've been looking at how the rotation of the Earth can be used to help understand day and night, and how the orbit of the Earth around the Sun combined with this rotation can help us understand seasons, and how the orbit of the Moon around the Earth helps us understand how eclipses work and moon phases. Now, these concepts, the idea that the Earth itself rotates or that the Earth is orbiting around the Sun, have not always been known. In fact, up until modern times, there were some very different ideas. So we're going to be talking about a bunch of history today. In order to help us out, I've got a really special guest, somebody who my wife insists is a pretty great guy. So a warm welcome to you. Well, thank you. I want to talk a bit about astronomy before Copernicus. Before the invention of telescopes and spacecraft and probes, there were still some observations that could be made about how the heavens worked, like the fact that every day the sun, the moon, and the stars rise and set. Like the fact that the Earth feels fixed, doesn't feel like the Earth is moving, like the stars don't ever seem to change, or the observation that things fall to the Earth. Based on these concepts, and based also on some philosophical concepts from the ancient Greeks, Aristotle, people hundreds of years before the Common Era, these ideas that the heavens are perfect and incorruptible, and as an added bonus, that circles are perfect. Based on these observations and on these philosophical assumptions, pre-Copernican astronomy had as its some conclusions that the Earth is the center of the universe, and that everything revolves in circles, perfect circles, around the Earth, because circles are perfect, and the Earth is the center of the universe. So here we have a visualization of this geocentric universe, with the Earth here at the center of the universe, the Moon going around the Earth, and then Mercury, and then Venus, and then the Sun, and then Mars, Jupiter, and then Saturn, each of them in turn orbiting the Earth, which is at the center. And I mean, this was the picture of how it was thought that the universe worked, based on the motions of the stars and the Moon and the Sun, and also the motions of the planets. But so we can go ahead and try and take a look at how this model worked and what some of the challenges with it were. Well, thank you, Professor. So we'd like to understand this geocentric model. Now, so far we've been using a heliocentric model, where the Earth orbits the Sun, the Moon orbits the Earth, and the Earth rotates. But if we take away these orbit lines and now fix our camera to the Earth, so the Earth is going to appear to be not moving, and we'll see what happens with the Moon and the Sun. This is taking the same model, but now just fixing the camera to the Earth, and we can just turn a heliocentric model into a geocentric model. So here's what we get. Here we have the Earth fixed, and now it looks like the Moon and the Sun are going around the Earth. And you'll see the Sun moves up and down as it orbits, and that basically reproduces the seasons. So this was the model that people had for hundreds of years. Actually, over 1,000 years. People believed in this model, where the Earth is fixed, the Moon and the Sun and the planets all orbit the Earth. But there were some challenges with this model, as we're going to see. So, first of all, we've seen this picture before already. This is the picture of the night sky with as the night progresses, the stars rise and go across the sky. And again, you can interpret this as the Earth is fixed and the stars are moving. And here we just see Mars rising. Now, this is where Mars is on a given day. This was, I think, what day we had, June 22nd. We can go and we can look at where Mars is each day of the year. So what we're doing, instead of going minute by minute, we're advancing each hour. So we're starting here at June 13th, 14th, 15th. And as each day goes by, we see the stars moving. And here we see Mars coming up now. So each day is advancing here. We're seeing Mars moving. And we'll notice that Mars is rising with the stars, but it's moving compared to the stars very slowly. We're seeing that Mars is a different place each night from where it was before. So let's try to understand that a little bit better. Let's lock on to Mars. So we're going to just search for Mars down here in the search box and lock on to Mars. So Mars is going to stay centered in our screen, and we're going to see how the stars are moving compared to Mars. So now here we're going to move again, and each night we're seeing that Mars is moving slower than the background stars. So each day, Mars is moving compared to the stars. But we're going to notice when we get into here in September, something funny happens. Mars slowed down and stopped, and now it's going faster than the stars. And then it's going to, when we get into November, it's going to slow down again, turn around, and again be going slower than the stars. So this is kind of strange behavior, isn't it? Mars is moving with the stars, but it's going faster than the stars. And then it slows down and it stops, and it's going slower than the stars. And it speeds up again, and it's going faster than the stars. That is a strange kind of behavior. Let's review what we just saw here. The planets move from night to night relative to the stars. The planets don't follow a uniform pattern relative to the stars. In fact, sometimes the planet is moving faster than the stars are going. Sometimes it's moving slower than the stars are doing. So you see this pattern in the sky where Mars is compared to the background stars, where it speeds up and slows down and turns around. This turnaround is called apparent retrograde motion. And it's something that we kind of need to understand. And the geocentric models of the universe didn't really do a great job in explaining it. So how did astronomers before Copernicus deal with planets' apparent retrograde motion? So we've already said that the ancients believed that everything in the heavens had to move in perfect circles. And yet we see, for example, Mars moving forward, turning around, going backwards, turning around, and going forward. The solution to this was kind of clever and a bit complicated, and we don't have to really understand it because it turns out not to be the way the universe works. But the idea they had was that, yes, the planets are orbiting around the Earth, but in addition to orbiting around the Earth, each of them is also orbiting around a invisible point in space, causing what's called an epicycle. So they are orbiting around the Earth, but then in addition, orbiting around an imaginary point in space. And so the planets do a cycle with an epicycle around it. And so you have these turnaround spots as expected. Kind of a random thing to add, but they found that if they added these extra cycles on top of the motions of the planets around the Earth and offset them just right and put the speeds just right, they could do a pretty good job at recovering in their models the actual apparent positions of the stars. It wasn't exactly right, but it was really pretty good. Now you'd say, well, why would you expect that the planets would be orbiting around the Earth, and but they'd also be orbiting around this fixed point, forming these weird cycles and epicycles? Because of their assumptions. The idea that the heavens are perfect and incorruptible, and that perfect circles are perfect. They conclude that you have to make the motions of the planets to be circles around the Earth. And so they came up with this complex pattern of circles that reproduced the locations of the planets in the sky over years and decades and even centuries. But along came a guy named Copernicus. He had a very different idea. Now, we say Copernicus came up with the idea. He was the guy whose publication of the idea really caught on. Had other people had this idea over the centuries in other places in the world, places perhaps even where they didn't have writing? Almost certainly. In fact, we know that there were some ancient Greeks who had come up with this idea, but their ideas never caught on. But Copernicus, again, came up with this idea, and this time the idea caught on. The time was right for new crazy ideas to begin to get some traction. Now, Copernicus' idea was this: the Earth is not the center of the universe. Not only that, the Earth is not fixed, but spins on its axis, the picture that we've already talked about. He said the sun is in fact the center of the universe, and the planets orbit the sun. Now, he still had this belief that they had to orbit in circles. He didn't have the idea that perhaps the planets could orbit in anything other than circles. So he still had the planets orbiting the sun in perfect circles, and that the moon orbits the Earth. So he came up with a model that did a pretty good job of reproducing the motion of the planets, but not perfect. In fact, it wasn't even quite as good as the old cycle and epicycle model. But the explanation for retrograde motion was a lot simpler. It made a lot more sense. It goes like this. So how does Copernicus's heliocentric model explain retrograde motion? Well, we know that the orbits of the inner planets are faster than the orbits of the outer planets. So here we see a picture here of Earth orbiting faster than Mars. Now, when we look from the Earth past Mars, we see different parts of the background star field, depending on where we are during the year. As Earth passes Mars, you see the angle between the Earth and the background stars changes. So Mars turns around and then turns around again. So what you're imagining here is this is the background stars. You can just imagine a bunch of stars drawn in that sphere. And as Earth passes Mars, the apparent direction between Mars and the background stars changes. So it looks like Mars stops, turns around, stops, and turns around again. And so this idea of the retrograde motion can be easily understood just from the orbits of the planets around the sun. So what's next? The next character in our story is a guy named Tycho Brahe. Tycho Brahe lived in the 16th century. He was a Danish nobleman, the heir to several, surprisingly, large estates, personal friends with the king, was granted an island in order to do his research on. He's an interesting character. At one point in his career, he got into a drunken duel with one of his friends when they were arguing about which of them was the better mathematician. And Tycho actually got his nose chopped off with his friend's sword. Rest of his life, he wore a metal fake nose. He was completely obsessed with astronomy. He wanted to make ever increasingly accurate measurements of the locations of planets in the sky because he wanted to come up with a better model of how the universe worked. So he spent most of his life doing stellar observations when he wasn't otherwise partying and being a 16th century aristocrat. Eventually, he kind of got in trouble and had to flee Denmark, partially because of some civil unrest caused by the way he was treating his workers. This is a guy we can't really relate to. This is someone whose worldview, whose reality is so foreign to us that you tell his story and it's like, none of this really makes sense. How could this be a real person? Well, things were a lot different in those days. But the thing that matters for Tycho Brahe, not his drunkenness, not his mistreatment of his workers, not maybe his grand vision for understanding. What matters was the fact that he made incredibly careful measurements of the location of stars on the sky, the most accurate to date over decades. He did a couple other really important things. He used parallax to constrain the distance to distant stars. Parallax. We're going to try and understand parallax here. I'd like to ask astrophysicists to do it, but he said he didn't have time, so I'm going to try and explain parallax. What is parallax? Why don't you try this experiment? Pick up your finger and hold it in front of your face and look past it. See your finger with one eye open, switch to the other eye, and then back to the first eye and to the second eye. Keeping looking past the finger, you'll notice the finger is moving back and forth. Yes? As you move the finger away, the amount it moves goes less and less. When the finger is close, it moves a lot. When the finger is distant, it moves a little bit. This is called parallax. When your point of view moves compared to background objects, the background objects move. Closer objects move more than distant objects, relatively speaking. And so if you change the locations of where you're taking a picture of something, you can use that to get the distance to a distant object. So Tycho Brahe said, if this claim of Copernicus is right, that the Earth is orbiting around the sun, then between the spring and the winter, the Earth will have moved an extremely long way. Because by this point, they knew how far away the sun was. It was a very long way away. So he says, if the Earth is in fact moving around the sun, the Earth is moving an incredibly long distance, then we should see some sort of parallactic angle change to distant stars. After all, we're changing the angle we're looking at them. We should change the angle where they're doing if we're actually moving. He did his experiment and he found no parallactic shift to distant stars. Now, there's two reasons this could be. Either one, the stars are unimaginably far away, or two, the Earth is in fact not moving around the sun. We don't know which. As things turned out, Brahe and others imagined that in fact the Earth was not moving, and that was the reason for the lack of parallactic angle. We know now that in fact the stars are incredibly distant. Another thing though that Tycho Brahe observed was a supernova. He was observing the sky night after night, week after week, month after month, year after year, taking very, very careful notes for whatever reasons he was doing it. And he discovers that a star appeared, got brighter, and then got dimmer again. Now this was not consistent with the kind of observations people have been making because, well, the heavens are supposed to be incorruptible, unchanging. If a star is appearing and then disappearing, how can that be if the heavens are incorruptible and unchanging? So based on his measurements, it became quite clear that current models had problems. His observations did not exactly match either the old Ptolemaic model with the Earth at the center or Copernicus's model with the sun at the center. They didn't exactly match. And supernovae were appearing, stars were appearing and disappearing in the heavens. That doesn't make sense if the heavens are incorruptible and unchanging. And there was no parallactic shift, which implied that either the stars were unimaginably distant or the Earth, in fact, was not moving around the sun. So there was clearly problems. Before he worked on trying to develop models of how the universe worked, his models didn't work that well. And he died having a great data set, but having not actually accomplished his goal of understanding how the solar system worked. But he passed his data on to a man named Johannes Kepler. Kepler was a very religious man, quite different than Tycho, who was kind of an aristocratic partier. Kepler had been a lifetime student and a very religious man. He took Tycho's data and attempted to find a better model to match it. Now, Kepler, he was concerned with the inaccuracy of the current models. His belief was that the models had to match the theory exactly, or the model was wrong. His belief, based on theology, is that God wouldn't do a half-baked job of planning the paths of the planets. So he believed there was an understandable and clear set of rules that God was using to place the stars in the sky. Now, that we would say that's a kind of a weird assumption to make. But science doesn't care why you make an assumption. Science cares, did you get it right? And how do you know if you got it right? If it matches the data. Kepler, after years of work, discovered that if you'd use a particular set of rules, really quite simple, then you could almost exactly predict the path of the planets. In fact, so accurate that they exactly fit Tycho Brahe's data. So what are Kepler's laws? Kepler's first law is that the orbit of a planet about the sun is an ellipse with the sun at one focus. So what is an ellipse? Well, an ellipse is a shape, a part of a family of shapes that includes circles. So let's take a look at this. Here we have a round plate, and when you look at it straight on, it appears as a circle. But if you look at an angle, the shape that you're seeing on the screen is an ellipse. So when it's straight on, it's a circle. When you're seeing a shape at an angle, that's an ellipse. Now, there's other ways to think about ellipses, other ways to make ellipses. What you can do is you can play this game, put two nails in a piece of wood, take a piece of string, tie between them. So there's one single piece of string that wraps around the pencil and comes down here. As I move the pencil along here, keeping the pencil keeping the both strings tight, it will form a shape which is an ellipse with the two nails at the two focuses. So again, we go back to Kepler's law. Kepler's law is that the planets orbit the sun with the sun at one focus of an ellipse, and the other focus is empty. And the planets travel along this elliptical shape. So we can take, there's some more things we can actually look about ellipses. So here we have a picture of a circle, and we have a planet that could be orbiting, and we have the two focuses. Now, as you move the focuses together, that forms a circle. As you move them apart, that forms an ellipse. The level to which it's an elliptical is called the eccentricity. So with the eccentricity is 0, it's a circle. And when the eccentricity is larger, it's more of an elliptical shape. Okay? So what's an ellipse? An ellipse is a kind of shape which, like a circle looked at an angle, it's a circle where you've the distance from the first focus to any point in the line plus the difference from the point of the line to the second focus is constant. So you can use that piece of string here and draw out the shape. When the eccentricity is high, it's more elliptical. When the eccentricity is 0, it's a circle. So that is an ellipse. So Kepler's first law says that planets travel in elliptical orbits where the sun is at one of the focuses and the other focus is empty. That's kind of surprising. Seems kind of random. We're going to see next class that it's not random. There's a really good reason for it, but it certainly seems random at first glance. Let's go on to Kepler's second law. Kepler's second law says a planet moves faster in the part of its orbit near the sun and slower when farther from the sun, sweeping equal areas in equal times. Again, let's try and understand this, but already it seems kind of random. So here we have the same simulation again, but this time we have the planet moving faster when it's close to the sun and then slower far from the sun. Faster, close to the sun, slower, far from the sun. Faster, close to the sun, further from the sun. So what we're doing here is 16 times per circle at very, very even times. We're starting a new section. And what you see, Kepler's second law says the area of each one of these things is the same. So this is a short, wide one. This is a narrow, deep one. This amount of time is the same as this amount of time. In other words, it's going much faster here and much slower out here. This is Kepler's second law. Kepler's second law says when the planet is close, we can play that again. Kepler's second law says when the planet is close to the star, it's moving quickly. When it's farther from the star, it's moving slowly. Again, kind of random. Nonetheless, if you assume this, you get extremely close to what you observe the planetary positions are. Kepler's third law. More distant planets orbit the sun at slower average speed, and they obey a very precise mathematical relationship, which I am not going to write down because you don't need to know it. But there is a precise mathematical relationship, you can look it up in the textbook, that describes the speed or the period of orbit of planets. Close ones orbit quickly, distant ones orbit slowly. We've already seen this back in the second lecture. Here we have Mercury orbiting more quickly than Venus, orbiting more quickly than Earth, orbiting more quickly than Mars, which is orbiting more quickly than Ceres, than Jupiter, than Saturn, going out, and all the way out to Pluto, moving actually very slowly. So this is Kepler's third law. Planets closer to the star move more quickly, and as you go further and further out, their speed gets lower and lower and lower. Again, this is something that Kepler observed to be true. It seems kind of random. But what's really great is if you assume Kepler's three laws, you can come up with a model that very, very precisely predicts the position of the planets in the sky, including the retrograde motion, well into the past and well into the future. So this was quite an accomplishment. So Kepler had come up with a set of laws that did a beautiful job in explaining the motion of planets. But his ideas were not accepted right away. There was so much inertia, thousands of years of belief that the heavens are perfect and incorruptible, that circles are perfect, and therefore that the heavenly bodies must travel in circles. The idea that the Earth is the center of the universe, that it is fixed and unchanging. These ideas weren't going to go away easily. But this is science, and in science you ask the question, can these assumptions be tested? Which brings us to our next character, a very famous man, Galileo. He was a pioneer in the design and manufacture and the use of telescopes. As well as that, he was an experimental physicist who did a lot of work studying the laws of motion and of gravity. With his new telescope, he made some really important observations. He observed that the moon has craters. He observed that Jupiter has moons that orbit it, and he observed that Venus has phases. And these observations turned out to be incredibly important. Based on these observations, he made the claim that Copernicus was in fact right, that the sun was at the center of the solar system, and the planets and the Earth orbited around the sun. Now, these ideas went against hundreds, thousands of years of teaching, and people were not ready to accept them. And toward the end of his life, he became very frustrated with the lack of progress, and in fact published a pamphlet arguing in favor of the heliocentric universe, in which, while some of his enemies argued that he was actually in fact trying to make fun of the Pope, that turned out badly. He ended up in prison, well, house arrest, till the end of his life, because he was trying to push these ideas that were just so different, and people were unwilling to hear different ideas, even though the data showed that these ideas were right. Eventually, his ideas won the day, but at the time, it was a challenging slog. Let's talk about these observations. So Galileo was a pioneer in the design and the production of telescopes. And he was one of the first people to use a telescope to look at the sky. And one of the first things he looked at, of course, is the moon. And looking at the moon, he made a rather remarkable discovery. He discovered that when you look at the moon through a telescope, you see that the moon has mountains and craters. Now, it had been assumed, as was mentioned earlier, that in the sky, everything is perfect. Everything is a sphere, everything is a circle, everything is eternal and unchanging. But if the moon has craters and mountains, not everything in the heavens are perfect circles and spheres. The second thing that he observed, looking at the sky with his telescope, is that the planet Jupiter has moons. And these moons orbit around Jupiter. So here's a picture through just an amateur astronomer's telescope of Jupiter and the four major moons. And if you come back the next night and the next night, you'll see the moons actually moving around Jupiter. Wow, that was an enormous discovery, because remember, the assumption had been that the planets, everything has to orbit the Earth. The Earth is the center of the universe. Everything orbits the Earth. But now you have moons orbiting around Jupiter. That breaks that rule. The second thing you saw is a little more confusing, but the thing that really nails down the idea that the planets have to be orbiting the sun. And that was the fact that Venus has phases. So here we have Venus in its new phase and then going through crescent back to a gibbous phase. And you notice that Venus is getting smaller as it's going toward the gibbous phase or eventually toward the full phase. And coming this way, it's getting larger. Also, what was really interesting is that as it's at the new phase and at the full phase, Venus is getting closer and closer to the sun on the sky. In fact, there's not any pictures here of it earlier than this gibbous phase because it's getting too close to the sun. The full phase, the new phase, happens when Venus appears the largest and close to the sun in the sky. The full phase happens when Venus is in line with the sun and when Venus appears the smallest. The full phase when Venus is in line with the sun. Now let's go back and remind ourselves how the sun phase, the moon phases work. Completely different than what you expect from this. So first of all, the new moon, like the new Venus, happens when the moon is in the direction of the sun. So the sun and the moon, and you see this new phase. That's because the back side of the moon is illuminated by the sun, and the Earth is seeing the unilluminated side. If we go to a quarter phase, first quarter phase, the moon is now far from the sun on the sky. It's 90 degrees from the sun on the sky, and we're seeing the quarter phase. When we go to the full phase, we see at the full phase, the moon is maximally distant from the sun. In fact, the moon is 180 degrees from the sun. You can't even see the sun and the full moon at the same time because it's on opposite sides of the Earth. Let's again compare that to what we saw with Venus, the new phase, and the full phase, are both when the moon is close to the sun. And Venus never gets to the far side of the Earth from the sun. The apparent size of Venus changes throughout the year. It's small during the full phase, and it's large during the new phase. Now, with the moon orbiting the Earth, the moon is always more or less the same size. Venus here is changing size drastically. So something is different about the phases of Venus. You can't go and say Venus is orbiting the Earth, because you would not get these phases. It would not behave this way if Venus were orbiting the Earth. So, but there does turn out to be, as you know, a really simple explanation that Venus is instead orbiting the sun. It's what we know now from radar and spacecraft and a million other observations. At the time, they didn't know. But Galileo looks at these phases and he says, there's got to be an explanation for this. And the explanation is the explanation that we know today to be true, that Venus is actually orbiting the sun. So here we are looking at Venus as Venus is orbiting the sun. We're seeing it go through the quarter phase and getting in toward gibbous phase. And as it gets closer and closer to the sun, it gets closer and closer to the full phase. And it got a lot smaller because it's a long way away. Now it's coming around, getting further from the sun. As it gets further from the sun, it gets in toward its gibbous phase and then finally a quarter phase. And then as it comes toward a new phase, it's getting larger and larger because it's getting closer and closer. And it's very large and very close to the sun at the new phase, and then goes away again. So the phases of Venus only make sense with this pattern where Venus is orbiting the sun rather than Venus orbiting the Earth, as was assumed previously. So this is pretty cool. So what's the conclusion of all this? So we had these observations that the sun, the moon, and the stars rise and set every day, that the Earth feels fixed, the idea that the stars don't seem to ever change and that things fall to the Earth. We had these assumptions that the heavens are perfect and incorruptible, and that, of course, circles are perfect. And based on these assumptions, these observations, there was the belief that the Earth is the center of the universe, that everything revolves in circles around the Earth, and that the planets revolve in circles within circles. And yet, increasing observations began to cast doubt on these ideas. There, as well as a growing belief, inspired in part by Kepler, that the observations should match the predictions perfectly, if in fact the model is correct. If the observations do not perfectly match the model, then the model needs to be let go. The first of these observations that I want to talk about, that we talked about, that really started to shake the foundations, was that new stars would appear in the heavens. Tycho observed the star appearing, was there for months, and then disappeared. The observation that the moon has mountains and craters. These two observations, the fact that stars can appear and disappear, the observation that moons has mountains and craters, cast doubt. In fact, made some rule out the idea that the heavens are perfect and incorruptible, since they clearly aren't. There was the observation by Galileo that there are moons that orbit Jupiter, and the observation that the phase of Venus shows that Venus, in fact, orbits the sun. This casts doubt on the idea that the Earth is the center of the universe, and that everything revolves in circles around the Earth. And then Kepler's models showed that if the planets moved in ellipses, following some very simple rules, then you could exactly predict the path of stars and the planets in the sky with no observable error. These ideas kind of ruled out the idea that the planets move in circles within circles, and instead that the planets and the Earth orbit the sun in elliptical orbits. Well, thank you so much for helping out. Oh, my pleasure. Anytime. So today we've looked at the history of how it was discovered that the sun is the center of the solar system and not the Earth. There were a lot of assumptions that people had made for hundreds and thousands of years that really seem to indicate that the Earth should be the center of the universe, that everything should move around the Earth. There were philosophical assumptions dating all the way back to Aristotle, that circles were perfect and the heavens were perfect. And yet there were issues. And we saw how these people were able to use scientific observations to show that the previous models were in fact incorrect, and eventually to show what the correct models were. And the development of these correct models led very quickly into a transformation in the way that we think about the universe. We're going to be looking at that a bit more next class. But even as these people, there's a couple things that I can kind of take away from this historical interlude. I mean, it's kind of weird looking at the history of people who we just really have nothing in common with. How do you understand what it's like to be a 15th, 16th century Danish aristocrat? And we hear about him, and it's like, it's hard to really admire much about him as a person. Yet science doesn't care. Science doesn't judge the heart. It judges the quality of the data. And this guy made incredibly careful measurements. And because of these measurements, another person was able to go and look at them and say, the models are wrong, and eventually leading to a much better understanding of how the universe works. So that's a really important thing to remember. Science does not care who you are. Science doesn't care what you think. If you're careful, if you take the observations and you look at them carefully, it will lead you to truth. And that is an incredibly encouraging thing, because it's oftentimes we can be wrong about a great many things. Science is a way that, despite our prejudices and our bad assumptions, we can find truth. Now, the second thing is related to this. We saw how Galileo faced opposition from entrenched ideas that were going back all the way to Aristotle. People like, this can't possibly be different. And they were, in fact, these ideas were so entrenched that even discussing the possibility that they might be wrong led him into significant trouble. So this is a huge concern that I have. So in your studies, in your research, and as you go into your careers, keep your eye open for those assumptions, for those statements that are just, you're not even allowed to think them. Because oftentimes it's in challenging those assumptions that we can begin to really learn about how the universe works using science which doesn't care what your assumptions are. Have a great week. And next class, we're going to look at how one of the greatest physicists in all of human history came to understand how, in a pretty great way, the universe works. We'll see you next class.